Alright, so in this lesson we're going to begin to look at our series circuits. We're going to calculate all the values for the series circuit that you see in our spreadsheet that I've created down below here in this area. Now, one additional thing that we haven't dealt with yet, but we're going to begin to deal with now, is our rules for a series circuit. So we can see here that the total voltage, there's going to be an amount of voltage dropped at each resistor depending on the size of the resistor, and the total voltage will basically equal those added up. Current in a series circuit is the same everywhere, so if we find the current anywhere, we find it everywhere. Resistance, total resistance, is just the sum of the three resistors added up, and power, it is the total of each power consumed per resistor. So here's our Ohm's law in all three forms, and our basic power formula in all three forms as well. So the first thing that we want to do when we begin to calculate one of these circuits like this is to fill in our known values. So what do we know? We know that we have 24 volts total voltage. What else do we know? We know that we have 1 k ohm on R1, we have 1.2 k ohms for R2, and we have 1.8 k ohms for R3. That's the only values we have at this time. So anytime that we get two of the three out of voltage, current, and resistance, we can solve for the third. We're always going to leave power to be done last. So for right now, let's just leave power alone and focus on the first three columns here. The first thing that I actually can calculate is my RT, because we see here that RT is equal to R1 plus R2 plus R3. So I can go ahead and calculate my RT. 1 times 10 to the third plus 1.2 times 10 to the third plus 1.8 times 10 to the third gives me 4 k ohms for my total resistance. I can go ahead and calculate my IT, and my IT, as we see here, would be equal to my VT over my RT. So my VT is 24 volts over my 4 k ohms. That gives me a total of 6 milliamps. So we can fill in that blank. 6 milliamps. What else do we know at this point? Well, our rules tell us that if we get current anywhere, we have current everywhere, because IT is equal to I1 is equal to I2 is equal to I3. So we actually can go ahead and fill in our amperage for every one of our values listed here. Now we have 2 of 3 in quite a few places. Go ahead and address this. If I know my I1 and I know my R1, I can go ahead and calculate my V1, and my V1 is going to be my 6 milliamps times my R1, which is 1 k ohm, tells me that my voltage drop here is 6 volts. For V2, I can just scroll up, change the value of the resistor to 1.2 k ohms, tells me the voltage consumed at R2. Scroll up, change the value again to the value for R3, shows me that I have 10.8 volts consumed for V3. Now, I can check my work that if V1, V2, and V3 add up to be 24 volts, then I did everything right in those calculations. And they do add up to 24 volts. So now that I have that, I can go ahead and calculate my PT. My PT is equal to my IT times my VT. My IT is 6 milliamps times my PT of 24 volts. And this gives me 144 milliwatts. I can go up here and do the next one. It's going to stay the same on the current at 6 milliamps times the 6 volts tells me 36 milliwatts for P1. P2, current stays the same, change the value of the voltage drop to the V2 value, gives me 43.2 milliwatts. Then we can change this to the final and last voltage amount, gives us our answer of 64.8 milliwatts. Now if all those add up, then we know we did everything right. Gives us 144 milliwatts. So that is how you calculate a series circuit. It's a basic series circuit. There are no random unknowns involved.